Next, we're going to be taking a look at a proof as to why the range of sine and cosine is what we looked at in the previous video, d minus amplitude, d plus amplitude. Some of you are not interested in proofs, and I get that, but I like them. So first of all, I want you to understand that we need to first make sure that there is an x value that guarantees that no matter what I do for b and c, I can get a maximum value of 1 for sine. So I'm going to take the arc sine of both sides. Arc sine of 1 is pi over 2, and then I'm just going to get x by itself by subtracting c and then dividing by b. So this confirms that there does exist an x value that ensures that I will get a maximum value of 1. Now if you try to increase that to 1.5, you'll find it will be undefined because there is no arc sine of 1.5, and that goes straight back to a unit circle. The highest value it can obtain is 1. Okay, there's another proof that involves calculus. I'm not going to go over it because you don't know calculus. The same proof goes for negative 1. Okay, there exists an x value that ensures that sine will be equal to negative 1 even if we introduce bx plus c in here. And again, that's the smallest possible value that sine can be on the unit circle, the y value of negative 1. Okay, so let's so we verified that there's an x value that ensures both 1 and negative 1. Now we're going to get into some nitty-gritty proof. Now suppose our a value is bigger than 0, so it's positive. Okay, we've already proven that this right here the smallest it can be is negative 1, right? So we're going to get a times negative 1, which is negative a. We're going to flip those, and we're going to get d minus a. Now, here's the trick. A is positive, right? So that means that the a is equal to the absolute value of itself. So I'm just going to replace a with absolute value of a. Now, we know for a fact this is going to be the minimum of the graph because it's d minus absolute value of a. Okay, exm stands for some extreme value, right? But now we know it's going to be the minimum because it's d minus absolute value of a. Again, there's another way of proving this using calculus, which I'm not going to do right now because you don't know it. Anyway, let's keep moving with the proof. Suppose a is bigger than 0. And now let's assume that, the biggest this can be is 1, right? We just showed that. So this will be a times 1, which is positive a, plus d. You get d plus a. Again, since a is positive, a must be equal to the absolute value of itself. So your maximum is going to be d plus absolute value of a. So there you go, folks. That proves that the range, when a is positive, goes from d minus amplitude to d plus amplitude. Now what if a is negative? If a is negative, the proof works the same until we get down to here. Since a is negative, negative a is equal to the absolute value of a. Now that can be confusing for some people, so let's choose an actual number, negative 3. Well, that would be, a double negative, and it would make it positive 3, but that's exactly what the absolute value bars do. So either way, you get positive 3. So negative a equals the absolute value of a. So when I have d minus a here, I can replace the negative a or the minus a with plus absolute value of a. Now this will actually give me the maximum value when a is negative. Okay, because it's d plus amplitude. The proof works the same similarly here. If a is negative, and I choose my maximum value of sine, which is positive 1, I get a plus d. Flipping that, I get d plus a. Here's another tricky thing that really throws people off. If a is negative, then a will be equal to the negative absolute value of a. Again, let's choose negative 3. If I plug in negative 3 for a, I obviously get negative 3 on the left. On the right, I get negative absolute value of negative 3, which is negative positive 3, which is negative 3. So either way, they're going to equal each other. So a is equal to negative absolute value of a, and I can replace it. And this demonstrates that when a is negative, if I'm looking for my biggest value here of 1, I end up getting my minimum of d minus absolute value of a, and that's because a flips the graph, and the top becomes the bottom, and the bottom becomes the top. So the minimum will still be d minus amplitude. So either way, the range of the function, we've just shown that the maximum, if a is positive, is d plus absolute value of a, and the minimum is, went too far, is the minimum is d minus absolute value of a. The same is true for when a is negative. The maximum is d plus absolute value of a, the minimum is d minus absolute value of a. So guess what? Now, I know I just did sine, but we know for a fact that cosine waves go from 1 to negative 1. It's exactly the same proof, so I'm not going to harp on that. The ranges are going to be exactly the same. Here, just to see visually, you can see that sine and cosine both go from 1 to negative 1. So the proof's going to work exactly the same. So anyway, the range will be the minimum and the maximum go from the minimum, which includes that, to the maximum. The range either way will be d minus amplitude, d plus amplitude, including those brackets. That goes for sine and cosine. That's it for this formal proof. If you have any questions about it, let me know.